So these these questions, particularly the first two starter questions, they were given to you because they are differential equations. That those you have already this morning solved two differential equations. You integrated dy by dx equals 4 plus 1 over x squared. You substituted a couple of values in and you worked out your plus c. So in a sense, you've been solving differential equations all along. A differential equation is simply an equation that's defined with a dy by dx. Okay, it's a mixture of dy by dx or dA by dt, something like that, as we'll have a look at this afternoon. And you integrate those and you work out the particular conditions. Now, two terms that we haven't really talked about in the course so far have been the difference between a general solution and a particular solution. Now, when I talk about the general solution of a differential equation, that's when you integrate your function and you leave the plus c. It's the general equation because it's got a plus c on the end. If we go a bit further and we're given more information, for example, when we're given y and x, we are then finding the particular solution to the differential equation because we've worked out what plus c actually is. All right, so we've got two things going on here, a general solution and a particular solution. Now, differential equations, obviously, they're a little bit more complicated than that. All right, you've been doing the basic ones so far. But differential equations can sort of be defined like this. Differential equations, they are equations involving a mix of variables and derivatives. So in the most basic terms, y, x, and dy by dx. And to solve these equations, basically, you're getting y in terms of x. You're getting rid of the dy by dx. How do you get rid of dy by dx? Through integration. So here is an example. All right, find the general solution. The general solution, all right, we're going to find the plus c. We're not going to work out what plus c is, but we're going to leave it in terms of the plus c. And the general solution to dy by dx equals xy plus y. Now, how is this different to the ones that you did in the starter questions, and how is this different from what you've done so far? You are integrating a mixture of x's and y's together. So what topic does this roughly tie in with what you've done so far? Well, you've done implicit differentiation where you differentiated x's and y's in the same function. Now, we don't have to worry about implicit differentiation. It's not like integrating trig where you have to bring in all your what does this differentiate to and test it and integrate accordingly. This is its own thing, but you can think of it as linked in a way to implicit differentiation. So to find the general solution to dy by dx equals xy plus y, we would have to integrate it, all right? And the temptation would be to say that, okay, so then y is just going to be the integral of xy plus y with respect to x, and that's absolutely right. But it's not the technique that we adopt, at least not as it seems what I've just written. So I'm going to clear that, and we're going to have a look at actually what we need to do. The first thing, all right, and there are steps to follow in this. The first thing, we're going to do what's called separate variables, and I can spell separate, I promise. So we're going to separate the variables. Now, what that means is we want everything to do with, in this case, because we're working with x's and y's at the minute, we'll stick with x's and y's. We want everything to do with y on the left-hand side of this equation, and we want everything to do with x on the right-hand side of this equation. All right, so that's what I mean by separating variables. We're going to eliminate the problem of integrating x's and y's together by separating them onto either side of the equation. So my initial equation, dy by dx equals xy plus y. If I want to move all of these y's over to the left, I'm going to have to factorize first. All right, so I'll take y out as a common factor over here, and I've got x plus 1. All right, and you might be able to see where I'm going with this. So now I want to get this y over to the left. And to do that, I'm going to divide both sides by y. So I've got 1 over y times dy by dx, and that's equal to x plus 1. Brilliant. So we've achieved what we set out to do. We've separated the variables. The second step is we are going to integrate with respect to x. All right. And we're actually going to integrate both sides of this. And that's what you've been doing all along. All right. If I just said to you, like in the starter question, dy by dx, say for example, x squared plus 4x, if you integrate both sides of that, you're integrating dy by dx with respect to x, and you're integrating x squared plus 4x with respect to x. It's just this little bit of notation here we don't ever actually do. Because when you integrate dy by dx with respect to x, you get y equals this. All right? So in a way, it's a bit of notation that we always skipped because it was unnecessary. But now it's necessary. So we're going to integrate with respect to x. We're going to integrate 1 over y dy by dx with respect to x. And we're going to integrate x plus 1 with respect to x. Now, here is another instance of, and you know, if I haven't said this already, I have said this already, then look at this dx on the bottom and this dx here, they cancel. And that's cancel in inverted commas. dy by dx behaves like a fraction, but it's not a fraction. All right, and I have said that numerous times. So when we integrate 1 over y dy by dx with respect to x, we're actually left with 1 over y dy equals the integral of x plus 1 dx. Okay. Now that allows us to integrate y, because we can only integrate y with respect to y. We can only integrate x with respect to x. So we're pretty much there. Integrate 1 over y with respect to y, you end up with the natural log of y. Integrate x plus 1 with respect to x, you get half x squared plus x, and then we've got plus c. Now you might be thinking, why didn't I put a plus c on the left-hand side? I mean, technically there is a plus c there, but you can think of it as if I'd written something else here, say I'd written a different constant, plus a, and I'd written a different constant on the right-hand side, and I'd written plus d. I could easily have subtracted a from both sides so that I would end up with d minus a. And d minus a is just another constant that we don't know, which is c. All right? And that's why we put the plus c just on the end. Now, remember, the idea of finding a general solution to a differential equation is to have it in the form y equals something. Okay? So let's do that, all right? To get this y out from its natural logarithm prison, if you like, we do e to the power of both sides. So we're going to do e to the power of half x squared plus x plus c. Now we're finished here, but we can make it look a little bit nicer. We can say y equals e to the power of half x squared plus x multiplied by e to the power of c. So now I'm going to apply a little trick, not a little trick, but I'm just going to say let e to the power c equal another constant a. All right, e to the power of an unknown constant is just another unknown constant, and so we end up with y equals a times e to the power of half x squared plus x. And there we have our general solution to a differential equation. So I'm just going to pause the recording for a second and take any questions from you guys. So, questions answered. Let's have a look at a different question. So I'll give you a second to read it. You can see that this is, you know, again, it's fitting the form of the last question. We have dy by dx. We have a mixture of x's and y's that are tied up with other functions. Okay, they're intermixed with each other. But we follow the same process, exactly the same process. Okay, so as is my wont, I always rewrite the question: 1 plus x squared dy by dx equals x tan y. Now, I forgot to write step 2 on the previous slide, but I will put it in this time. So, again, step 1, separate those variables. Okay, now I hope you're kind of trying this along with me. We're going to separate those variables. We want everything to do with y on the left-hand side. We want everything to do with x on the right-hand side. So I can see that we can divide both sides by tan y. And I can see that we can divide both sides by 1 plus x squared. So it's the same differential equation. I've just rearranged. All right. So now all my y's are on the left, all my x's are on the right, obviously with the exception of dy by dx. Second step then is we integrate both sides with respect to x. And we end up with the integral of, now 1 over tan y is cot y. And then we've got this x over 1 plus x squared dx. So we've integrated both sides with respect to x. Now that's important because I know we end up with integrating y with respect to y, but it's because of this step here. If you were to leave out a step at any point, it would be writing this out. Okay, you can go from this line here, the second line, to what I'm about to write, okay, which is the integral of cot y dy equals the integral of x over 1 plus x squared dx. The examiner's not necessarily looking for you to add in this little piece of knowledge. It's fine to go from line 2 to line 4 here. All right, how do we integrate cot? Well, cot is one of our given results in the formula book. All right, if you integrate cot, you get log of sine. So we don't need to go too further into details, messing around with identities or anything like that. It's not one we have been asked to prove in this question, so we can just go ahead and use the standard result. Excuse me. So we integrate cot y with respect to y. We end up with log of sine y. Okay, there's no multiple on the y here, so there's no fraction in front. Remember, the plus c is going to be whacked on at the end. Now, integrating x over 1 plus x squared. This is where, one thing that differential equations does have is you'll be asked to integrate using all of your toolbox. Okay, is it a partial fraction? Is it a trig identity? Is it a guess, differentiate, adjust? What is it? Here we have a fraction, and what do we do when we have a fraction? We've got a couple of options. Is it a partial fractions? Doesn't look like a partial fractions because we can't really turn this denominator into a product of two functions of x. So reverse chain rule is another thing we use with fractions. And the reverse chain rule works if we can differentiate the denominator to have something like the numerator. So if we differentiate 1 plus x squared, do we get something like x? We do, we get 2x. All right. So we can actually integrate that by saying it's 1/2 of the natural log of 1 plus x squared. Okay, so that's that guess, differentiate, adjust. So now we have plus c on the end. Now there's something to look out for here. Okay, and although there is a set method for differential equations, you still have to use your intuition, your maths knowledge to try and think a couple of steps ahead. And what I'm thinking here is this plus c on the end. Well, the rest of the equation is in terms of natural log. So it makes sense to say, instead of plus c on the end, and the rest of it remains the same, so instead of plus c, I'm going to write natural log k. Now what that allows me to do is it allows me to combine this half log 1 plus x squared and the constant. All right, c is a constant we don't know, so it can be written as a natural logarithm of another constant that we don't know. So let's go ahead and combine the logarithms then. So we've got log of sine y equals 1/2 log. What do we get when we add two logarithms with the same base? we multiply them together. So we've got k 1 plus x. Oops, I've skipped a step. You might be able to see it. Oopsie daisy. After me saying you need to be careful with your logs, there's something else we need to do first. And I'm sure you're way ahead of me, but it's this. We need to use the power law before we use the addition law. So this power of a half, this coefficient, jumps up and becomes the power of 1 plus x squared. Okay, so we've got log of 1 plus x squared to the half, or log of root 1 plus x squared. And then it's plus log k. Getting ahead of myself there. So then log sine y, and you can combine some of these lines together. You don't have to write every single line. This is just really explicitly outlined in the process. So then we've got natural log, use the addition law, k multiplied by root 1 plus x squared, and we're off and running. So that means that sine y is going to be equal to k root 1 plus x squared. We've just done e to the power of both sides. The natural logarithms have disappeared. And then y, because we should have it in terms of y, and we literally just write arc sine. Okay, k root 1 plus x squared. And there is the general solution to our differential equation. So again, I'll pause the recording. Feel free to ask any questions. All right. So hopefully that made sense, and hopefully you were way ahead of me when you realized that I hadn't used the power law before the addition law. Right. This one, I'm going to give you a bit of a head start with. You'll see that we're finding the general solution to this differential equation, but then we're asked to go one step further, and we're asked, given that x equals 1 when y equals 4, this is exactly like the starter questions, then leave your answer in the form y equals f of x. All right, so this time we're going to have to work out what the plus c is. That's effectively what's going on. If you have a look at this, when you separate your variables, you might be way ahead of me here, but you'll be able to predict. You've got 2x plus 1 multiplied by x plus 2 as a denominator. And you're going to have to think about what's the best method of integrating that function. So I'll pause the recording again, and I'll give you guys a few minutes head start before I launch in and start talking it through. Okay, so I'll start talking through this one. Again, just put me on mute if you just want to work through it and watch my working appear as if by magic, but I'll just talk through. So same as ever, okay? We're going to start by separating our variables. Minus 3, minus 2, 2x plus 1 times x plus 2. So step 1, separate. So we're going to have 1 over y minus 2 dy by dx, pardon me, equals minus 3 over 2x plus 1 x plus 2. So we've got all of our y's on the left, we've got all of our x's on the right. Job done. Step 2, we're going to integrate. Okay, integrate both sides with respect to x. Now I'm going to skip out that line of working this time, and I'm just going to write 1 over y minus 2 dy is equal to the integral of minus 3 over 2x plus 1 x plus 2. Now, how do you integrate minus 3 over 2x plus 1 times x plus 2? We've got to use partial fractions. All right, that's our technique in integration. Remember I said this will bring all of your tricks, all of your integration tricks together. You can be surprised by any sort of question. So we're going to use partial fractions here. And you will be rewarded with marks for this, so don't worry. So partial fractions then, we've got minus 3, and I'll just put that as minus 3 on the top. 2x plus 1, x plus 2 is the same as a over 2x plus 1 plus b over x plus 2. So therefore, minus 3 is the same as a times x plus 2 plus b times 2x plus 1. Now we can let x equal minus 2, which means that minus 3 equals, this is eliminated. 2 times minus 2 is minus 4, plus 1 minus 3. So therefore b is 1. We'll let x equal minus 1/2. So we've got minus 3 equals minus 1/2 plus 2 is 3/2. And that's right, isn't it? Minus 1/2, 1 plus 2, yep, minus 2, sorry, 3/2. So minus 2 equals a. So then we rewrite our integral before we actually integrate it. So 1/y minus 2 dy equals, so a is negative, so I'm just going to switch the fractions around. So I've got 1/x plus 2 minus 2 over 2x plus 1 dx. So I've used my partial fractions. It's time to integrate. Natural log of y minus 2. Remember, no plus c on the left-hand side, it all goes on the right. Integrate 1/x plus 2, we get natural log of x plus 2. And then minus natural log of 2x plus 1. Remember, if we differentiate natural log of 2x plus 1, we get 1/2x plus 1 multiplied by the 2 using the chain rule, which is what we wanted. So it is just natural log of the 2x plus 1. Because everything else is in terms of logarithms, I'm going to write my plus c as natural log k. All right. So separated variables, integrate both sides. I use partial fractions for my fraction in order to integrate it, and I've written my constant as a natural log because everything else is a natural log. Okay, let's tidy up. Natural log y minus 2, we'll use our laws of logs. Remember, we've got take away this, add this. So when we're using BIDMAS, we just do what comes first. So we end up with natural log of k x plus 2 over 2x plus 1 on the right hand side. Okay, so that then shrinks down to just be y minus 2 equals k x plus 2 over 2x plus 1. So then y is x plus 2 over 2x plus 1 plus 2. So there is our general solution of the differential equation. All right. Now the question didn't want the general solution, it wanted the particular solution. All right. So we were given some boundaries. We were given x equals 1 and y equals 4. So when x equals 1 and y equals 4, we're going to substitute those in and we're going to see what we get. So that means 4 equals k multiplied by x plus 2, so 3, divided by 2 lots of x plus 1, which is 3, and then plus 2. Yeah? So 4 is just equal to k plus 2, so therefore k equals 2. Let's just check we got that right. 1 plus 2 is 3, 2 times 1 plus 1 is 3, then 2. So we've got k equals 2. Now all we have to do at this stage is rewrite the equation as requested using a value of k. So we've got 2 lots of x plus 2 divided by 2x plus 1 plus 2. Now we can combine all that together because we can think of it as 2 lots of x plus 2 over 2x plus 1 plus 2 lots of 2x plus 1 over 2x plus 1, and we can just combine that accordingly. So 2x plus 4, 4x plus 1, we got 6x, I think, 2x plus 4x, 6x, plus 4 plus 2 plus 6. with 2x plus 1, which simplifies down to, yeah, we can't really do much more with that. So we're just going to have to say it's 6 lots of x plus 1. 2x plus 1. And there is our particular solution to the differential equation. Okay, question done. We started with a differential equation, we separated, we integrated, we used partial fractions for that integration, we found our general solution, we substituted the values in, and we found our particular solution. Now it should be said that you can take this x and y value and substitute in whenever you want, all right? You might be better off substituting in as early as possible, so you could substitute here and work out what k actually is. You could substitute y equals 4, x equals 1, x equals 1, and you get the fact that k equals 2 from there. And then you can combine the logarithms together to get your particular solution. There's nothing in the specification or anything that says you must find the general solution and then find the particular solution. All right? You can do it early, you can do it late. All right, so I'll pause the recording again and I'll take any questions from anybody. For the recording, here is a further question. To solve the differential equation, it's exactly the same process. Separate the variables, integrate both sides, find your general solution, substitute your x's and y's in, and find your particular solution. If you are just watching this back on a video, then pause the video, do the question, and then come back, because I am about to reveal the mark scheme. I hope you paused the video. Here is the mark scheme. Oh, different question. Nuts. Here is the question I want you to do if you're watching the video. Forget that last question. That was just an extra one. Here's the question I want you to do. Separate variables, integrate, substitute, write it in the form you asked. Pause. And there's a mark scheme. Yay, full mark scheme. Right, I'm going to end the recording.